Welcome back, class. We will continue with chapter 5 on MOSFETs. So in the previous recordings we addressed the first three sections of this chapter, and we have two more sections to go, and then we are done. Now there's more sections in the chapter. As I mentioned, those will be handled in your next course. So as far as we are concerned, we have 5.4 and 5.5 left to do the theory and then some of the problems. So let's look at 5.4 now, and this is your introduction to using the MOSFET as an amplifier. And then the next section, 5.5, does a little more detailed analysis of the small signal part of it. That means we kind of ignore the DC, the biasing, and then only worry about how much amplification, linearity, etc. We can get with small signal in the input side. So 5.4, we've got these 6 topics, and I'm on slide 43 of the PowerPoint. So we have voltage amplifier, then voltage transfer characteristic, VTC. Then we talk about biasing for linear operation. We briefly introduce small signal voltage gain, then some graphical analysis and locating the Q point. So these are the topics, and if you compare this to the previous chapter we studied on BJTs, you'll find exactly the same listing of topics. So like I said many times before, everything about the MOSFET chapter follows almost parallel to what we did with the BJTs. Okay, so I'm going to move on to slide 44, where we introduce the idea of a voltage amplifier. Now, on the input side, we have the gate to source battery, right, or gate to source voltage. On the output side also we would like a voltage. So far though, all the relationships that we have studied between the input and the output basically is the output is the drain current ID and the input is the gate to source voltage, and so the relationship was not exactly voltage to voltage, but it was voltage to current. So but it's easy to change a current to a voltage by running it through a resistor and then picking off the voltage across the resistor. So the bottom line is we want to create a V out by V in type of relationship that compares the ratio of two voltages. So to do that, we introduce this circuit that you see in the drawing, where we take the output, which is actually VDS, drain to source voltage, as the difference between a fixed VDD, which is the battery, the biasing battery VDD, connected to the drain in this configuration, in this circuit, and then you subtract the ID/RD. So this is just KVL for this right side circuit, and from here we get an equation for ID, which we already know because we have used it many times before. But now if you write it in this form that I put in the red box, what we are saying is the output is proportional to the one independent variable here, which is the VGS, right? Everything else is kind of a constant. The resistance is a constant, Kn is given, Vt is a constant, VDD is a constant. So you can see that we are writing an output as being proportional to an input, right? And so that is the kind of amplification relationship that we want. One other thing that I'll mention here, because this becomes important later on to remember, as VGS increases, ID increases, right? Because the relationship is a direct proportion. It's actually a square relationship. So ID is proportional to the square of VGS. So as VGS increases, ID will increase in a square way. But because we are interested more in VDS, not so much ID, VDS has the opposite relationship, right? As ID increases, VDS falls. Hence I say as VGS increases, ID increases, but VDS falls, okay? So just remember this inverse relationship because we will see it again in the next slide. So I'm on slide 45, and here we are introduced to something called the voltage transfer characteristic, which is basically a relationship between the input and output voltages, okay? So if the input voltage in this amplifier is VGS and the output voltage is VDS, it's an inverse relationship, as I just told you in the previous slide. So as VGS increases, we expect VDS to fall, but it's not a straight line fall. There's all kinds of little factors here that change the shape. And it also depends a little bit on the physics of the device, the behavior of the device at various voltages, and so all that is captured in this voltage transfer characteristic, okay? So let's spend a couple of minutes quickly going through this because this is an important concept. So first of all, you have the circuit with the input and the output, and I have repeated the formula for VDS. Again, remember, as VGS increases, the current increases, but because the current increases, this voltage drop VDS decreases, okay? So the same regions that we have become familiar with now, the triode region, the saturation region, the cutoff region, all three are shown here, even though the relationship is now between VGS and VDS, right? Previously, when we were talking about graphs, we generally only looked at VGS and IDS, right? And we saw the saturation zone. Actually, I'm going to go back a couple of slides, a few slides, just to show you what we looked at previously. So, for example, I'm on slide, slide 16 is where you see previously what we studied, right? To understand the triode region and the saturation region, we had the VDS to ID relationship, okay? So where there we understood that as VDS is low and slowly increases, while it's still low, it is in the triode region, and once VDS reaches the overvoltage, it starts to straighten out, becomes flat, and this region we call saturation, okay? So this was the previous kind of graphs that we're used to. So I'm going to go back to our slide. Give me a second. Okay, I'm back on slide 45. So same the regions, the triode region and the saturation region and the cutoff region, right? This time we are coming from this side. So VGS, as it increases, we know that VDS falls, or to put it another way, VDS is very low in the beginning, right? It's so low that, or actually for this portion 0 to VT, it's better to focus on the VGS, right? That is the gate bias. So we know that unless the gate bias goes above the threshold VT, really nothing's going to happen, right? You are not creating that capacitance, you're not storing enough charge, no current. So that whole region is cut off. So that is when this VGS is very low. But after that portion, we start focusing on what happens with VDS, and we know that when VDS is very low, which is the triode region, if VDS is less than the overvoltage, it's a triode region, and that is what is shown here. And then as VDS rises, it goes into saturation, and we have this nice saturation region. So we have these three regions, and I've tried to define each one of them to the right side here. The cutoff, the saturation, the point B. So as you're coming from this side, you're following the graph as it falls down, you have the cutoff region where we are flat, until Vt nothing happens, saturation region where VGS exceeds Vt, and then the triode region where VDS falls enough that it's not in saturation anymore and we see the triode. And the point B is important to know where we transition. I mean, we already know that. We say that's the point where the drain to source voltage equals VOD, and there's a couple of formulas that are used in problems to come up with that B, in addition to knowing that VDS equals VOD. If you didn't want to measure VOD, then you can use these formulas. And then there's the triode region where VGS has to be greater than VT, no doubt, right? But VDS is less than overdrive. So spend some time, try to become familiar with the ideas behind this because they can be useful later on. Okay. Moving on to slide 46. Now we talk about biasing and the Q point, right? Again, this initial discussion about this, we had it when we studied diodes, we had it when we studied BJTs, the same idea. You need to pick a point on the voltage transfer characteristic, the VTC, so that you have linear operation if you go slightly on either side of that point. So if you pick a point Q and you want to go slightly above and slightly below, meaning you're taking the input signal slightly less and slightly more, that slightly less, slightly more is what's called small signal, right? So if you operate in that small signal area, you want to be in the linear portion of this graph. So this graph is not linear here, as you can see. It's not linear here in the triode region. It's only linear here. So you need to pick the right Q. And so that is a big part of amplifier design, and that's why we keep repeating it so we all understand it. So what is the importance of Q? Q is determined by the value of VGS and that of the load resistance, right? So given this circuit and given a certain VDD, we need to know what VGS will be and we need to know what RD will be, because once we know RD, we know what VDS is, right? So Q is determined by the value of VGS and that of the load resistance. More importantly, Q depends on the required gain and the allowable swing at the output. So how much do you want the output to swing? How much gain do you want? Do you want it to be 5? Do you want it to be 10? Because the more steep this is, the more gain you get. But you also have certain limits on how much is achievable. So many factors come together. Remember, we used to have beta and alpha in BJTs. For MOS circuits, we don't have beta and alpha, but we have certain other things, such as, for example, the aspect ratio, width to length ratio, right? That is one factor that you can control. So, and then of course you can control the biasing so that you can swing up or down. So these determine, how you can match the circuit to the goal of getting a certain amplification. We'll study much more about, you will study much more about amplifier design in your next course. In this course, my duty is to introduce you to the basic ideas and to make you understand the operation, the physics behind the BJT and the MOS. So hopefully, you're getting that knowledge. Okay, moving on to slide 47. Here we bring in the idea of biasing for linear operation and introduce also the idea of voltage gain. Okay, we will spend more time later on the small signal aspect, but you will now for the first time see this circuit with the biasing voltage, the DC voltage, VGS, separate from the small signal, right? Now you've seen this for the BJT, the same idea is here. We try to think of it as two separate sources of excitation so that we can use our favorite formulas from the principle of superposition, right? Superposition is so nice. It says if you have multiple sources, you only have to study the effect of one source at a time and just add it and you get the total output. But remember, to be able to do that, your circuit has to satisfy the condition of linearity. That means if it is only a resistive circuit, it's always linear. But once you have these devices like diodes and BJTs, linearity is only possible with certain conditions. Some combination of currents and voltages only give you linearity. Okay. So what are we showing here? So we are showing this nice little input on this side, on the left side, VGS, and that's why you see those the way we name it, V, small v, GS, both small, right? Small characters. That means that's the signal. The big V, the big GS means the battery, the biasing source. Similarly, VDD is the biasing voltage on the other side, because you always need two sources, right, to make these three-terminal devices operate. For a diode, you only need one voltage, but for these devices, three-terminal devices, you always need two sources, right? Okay. Sometimes, well, I'll just stop there. So the input voltage, the signal, if it is small like this, and if you keep the operation to this region, the linear region, then as you can see from the graph, you get a much larger signal on the output. So there is nice amplification, and there is a phase shift also. So as you go low to high on the output, you go high to low. Okay, so there's generally a negative, an inversion. Okay, so what I'm saying on the right side here is, if the signal to be amplified, VGS, it's a function of time generally, as you can see, this is time varying, is superimposed on the bias voltage VGS. Total instantaneous values by superposition is small VGS, that is the sum of big VGS and small VGS, you get small v capital GS T. So try to remember this way of writing. So this is VGS plus VGS, okay? And if you meet the small signal condition, and what is the small signal condition? The signal has to be less than twice V over voltage. So this is an important condition. This is probably the first time you're seeing it, but remember this, because this applies everywhere. You'll have to keep checking to make sure that we are indeed small signal. So assuming small signal, meaning assuming we meet this condition, then you can write the current also as the sum of the DC current plus the signal current. And the DC current is shown as ID, and the signal current is shown as small I small d, and the total is shown as small I big D. Okay. And what is the small I d? How do you find it? You find it like this, which is similar to other formulas we have used for ID, right? You've seen the ID formula many times, so I won't repeat it, but basically ID always consists of this factor K, the process parameter, this voltage, the overdrive voltage, and also the gate to source voltage. Okay, so the same thing is repeated for the small signal, and as the same format existed for the big ID also. Okay, so that is this slide. I will move to slide 48 and actually talk about small signal voltage gain, right? Now what is the voltage gain? It's the output voltage by the input voltage, right? So going back to the previous slide, that would be VDS by the input VDS, right? Or VGS. So if you take that ratio, you get the voltage gain. But generally when we talk about voltage gain, we want to restrict it to the signal gain, right? So the small signal voltage gain can be found like this. it still depends on pretty much all the main factors, meaning the process parameter which has a minus sign. There's a process parameter Kn, process transconductance parameter Kn. There's the VGS minus VT, which is also the overdrive voltage, which is the input side, and then there is the resistance RD. So there are many formulas for this gain, and at different times we'll use different formulas, but try to remember that this is how to write it. Now you can also write it as this minus IDRD by VO voltage by 2. You can substitute here and you come up with this. All these derivations again are in the chapter in the textbook. You can read through them, but these three are important to remember. Okay. The next slide, 49, is an example, and I don't want to do the mathematics yet. We'll come back in my next recording and look at some problems. But basically, as you would expect, in this example, we are given a lot of things such as VT, the aspect ratio, the process parameter, and then some ID, VDD is also given, RD is given. A lot of stuff is given, and we need to find the voltage gain and some currents and resistances. But the important thing we're calculating here is the voltage gain. Okay, and then we know the voltage gain. The second part of the question says how much are we allowed to swing on either side. That means what can be the peak to peak value of the signal so that we are still linear, right? You would expect such a question to be very important, and that is the question we are being asked here. How much, what can be the magnitude of the signal? So we'll come back and do this in a little bit. Another problem on what is the maximum gain, same thing, right? You don't want to run into nonlinearity. You want to stay in the saturation region for this and MOS type circuits. So that's another problem. Yeah, here's one more set of graphs which are important to show us in a practical way how to create the VTC. That means you don't actually necessarily have to do too much work on the bench in your lab to create the VTC. Is it possible to do it quickly just using paper? And the answer is yes, because these blue lines, they are given by the manufacturer of the MOS, of the NMOS or PMOS transistor. So you can get these characteristic curves. Then all you need to know is your load line, which I've talked about it enough in the past. If you have a known VDD and a known RD, you can create the load line as a straight line, right, using the y equals mx plus c approach. And then you put the load line on the manufacturer's graphs, and each point you can pick up, right, from here. And so you can transfer that to the VTC. So each point here gives you a specific value of VDS and VGS, right? So let's say this point, right, where the Q is. So there's a VDS and there's a VGS. Let's say at this point, right, if you draw another straight line here, you have a certain VGS and a certain VDS. Similarly here. So you can take all these together and then you can plot it and you'll come up with the VTC. So either of these are okay people don't use this too much, but actually I think I showed you an example with the BJT where you can even do your analysis just on this graph. So you can actually do the analysis on 3 different graphs. You can do it with this relationship VDS times to ID with these graphs, with these straight line sections, as given by the manufacturer and the load line. So this is one approach. You can put your input signals here, right, and take the output out of here or out of here. That's one approach. The other approach is to use the VTC. There's another third approach I'll show you in a little bit. But all these are to help us design manually. Now, these days you can use a computer program to do all this. So it's not, you can run a simulation and have the answer. But you have to understand how simulations work, and the simulations also use this data that you're looking at now. Okay, so this is supposed to teach you how to create the VTC just from the manufacturer's data and the load line. Okay, I think that ends section 5.4, and so we move on to section 5.5, where now we will focus more on the small signal operation, create some models, and you've seen the benefit of having a model. Previously, I think when we studied BJTs, we noticed this. If you have a simplified model with only resistances and some, dependent sources like a dependent current source or a dependent voltage source, the analysis becomes pretty simple. You can just use Ohm's law and KVL, KCL, voltage divider formula, etc. to solve for various conditions, amplifier conditions, using these devices, NMOS device or BJT devices. But to build the small signal model, you have to study this section of this chapter. So that's what we'll go through. Okay. All right. So I'm on slide 52, and you can see there's about 8 sections here. So let's quickly run through those before we run out of time. So I will move to slide 53, and here again we start with looking at the bias point, the DC bias point. But in this case, we are looking at another graph. Right? I told you there's 3 ways to look at the input-output relationship, small signal, for a given device. So we saw the VTC, we saw the other one that relies on the VGS lines. This one, we rely on this VGS versus ID graph, right? This graph, you may remember, as here we kind of keep VDS constant or assume VDS is constant, and as you gradually increase VGS, what happens to ID in the circuit, right, is what we don't have to keep VDS constant, VDD is constant, but with VGS we know ID increases in this fashion because of this square relationship, right? So we plot that, and then based on that also we can look at the input versus the output, but the output here will be only current. So the input is a voltage, but the output is a current. So it's not a clean amplification, right? Ideally, you want the output and the input to be the same so that you can come up with a nice gain factor. But here what we'll come up with is something called transconductance, right? A conductance relates the input voltage to the output current. And so we have to learn about MOS transconductance. It's a very important factor that we used in BJTs, and we'll use it here also as we design or we create the small signal models. So let's go ahead and understand the definition of GM, the MOS transconductance. So again, the graph is VGS to ID, and it's in this form. As you can tell, this is the cutoff region, very low VGS. It's even less than VT, no current flows because the device doesn't turn on. And once it's past VT, boom, you start, current starts to flow, and we enter the triode and the saturation region very quickly. So what is VGM? VGM is the slope at a certain bias point where we assume, we are thinking that it's an almost linear segment, right? So you don't want to put a Q here and put a graph there because it's not linear. You can see it's curving, but this portion certainly seems like it's linear, and then it's curving again. So if you pick a reasonably linear point and you draw a tangent, the slope of that tangent is called GM. So that's useful if you're using graphical methods, but a better definition of transconductance is, for a given VGS, right, for a given VGS here, at the Q point, what is the output current? The output signal current, not the total current, okay, not the total ID, I capital D, no, I small d. So the ratio of I small d over small v small gs, that means this signal, that ratio is called the MOS transconductance. It's devoted by GM, and there's a couple of formulas for it. So it depends on this Kn, the process parameter, and it depends on VGS minus VT, which is also the over voltage. So you write it as GM equals Kn VOV. Now all this is true only if you satisfy this small signal condition, okay. So this we will use quite a bit, and you can also see how the input signal is amplified here using the same graphical approach, okay. Alright, so that was introduction to transconductance, to more of the same linear signal business. I will move to slide 54 and let's see what we have here. So now the voltage gain that we previously defined, small signal gain, now we again come back to looking to see if we can improve on it and create one more relationship. Yes, the relationship is that the small signal voltage gain is nothing but the transconductance times Rd, okay, and it is nothing but the ratio of the output voltage by output current, output voltage by input voltage, right, VDS by VGS. Now that's a nice little ratio that we find comfortable, useful, but to get there we have to multiply the transconductance by the resistance in the drain circuit. This we have seen before, right, the lower one, but I just brought it here so that you can see both of them with relation to each other. Now you know GM equals KNVOV, right, from the previous slide. So I hope you can see that they're all connected to each other, okay. And here there's a nice graphic that shows you the input signal, the output signal, and why you have to be in saturation to be able to do that. So pay some attention, and this gives you good insight, okay. So the output is shown to be GM times RD, this factor times the input times V. If V you assume is the input, then GM RO times V is the output, okay. Alright, so I'm going to move, yeah, and there is this factor also, the fact that V by 2, right, the peak voltage or half of peak to peak voltage has to be less than 2 times V over voltage, okay. Alright, next slide 55 also introduces an important factor or important condition. I think you're used to it by now, so this shouldn't come as a big surprise, and we've just repeated it. We are repeating it. I've already introduced this just a few minutes ago. Separating the signal in DC quantities. Under the small signal approximation, that means if you meet this condition, signal quantities are superimposed on DC quantities. Superimposed meaning superposition, right? VGS, for example, VGS can be written as VGS plus VGS. ID can be written as ID plus ID. V drain to source, small v drain to source is the total, is a sum of the DC value, which is big V big DS plus small v small ds, right? So get familiar with this format because this is helpful, and you can expect to have to solve problems, etc., using this. So once a stable DC operating point has been established, that means we have picked a good Q and all DC quantities are calculated, we may then perform signal analysis ignoring the DC quantities. So first step, do the Q point analysis. In fact, I'm going to see if I can write Q here so that we remember. Okay, so once a stable DC operating point has been established and all the DC quantities are calculated, then we are done with that portion. Now we can actually ignore or take them out, and you know how to take them out, right? You can short a voltage source or open a current source and focus only on the DC signals and solve. So that is what is being summarized in this slide. Okay, so we'll move to slide 56, where we are introduced to the small signal circuit models. You've seen this before, the idea of a circuit model, so I won't repeat it too much here, but we have the same pi model. They call it the hybrid pi for some reason, but you recognize it looks like an inverted pi, right? So here is the main model. Compared to having a diode here in the BJT, here we leave the input side, which is the small VGS, small v small gs, which is the gate to source side where we have the signal, we leave it open. Why? Because we know that the MOSFET is a unique device where no current actually flows in the gate circuit. I hope I have mentioned this before, and so I am reiterating it. The gate current is always zero. In a BJT, that's not true. The base current is never zero. There's always a small base current. But in MOSFETs, NMOS and PMOS, the gate current, there's always a gate voltage, right? VGS or VSG if it is a PMOS circuit. But no current flows into that circuit. So because no current flows, it's almost like an open voltage or an open circuit, and so we leave this open, and then on this side the model shows you a voltage controlled current source, right? This is a dependent source, it's a current source, a dependent current source. What does it depend on? It depends on a voltage. What is that voltage? It's the signal on the input side, the gate side. Okay, so this is the drain and this is the source. So the drain to source current is what is shown, is the only important thing here, and that is modeled as a transconductance times independent value, which is the small signal. Okay, on the right side it's a slightly more complicated because we introduce the RO, the output resistance. This comes about if we are asked to include the effect of the channel length modification, right? As I told you, once you get into deep saturation, something happens to the device and that makes some of your earlier formulas not applicable, meaning they become more complicated because now you have to bring in new factors such as lambda and so on. So to account for that, there's a new factor introduced called RO, and that factor, without RO, you can imagine a resistance, an infinite resistance, right, an open circuit. But once you have to include the channel length modification, that means the problem tells you that in these circumstances or with this device, lambda is not 0 anymore, lambda has some value, so start using it. Then you have to put this RO. Now I will show you the relationship between lambda and RO at a later point, or maybe I showed it to you already, lambda and voltages. Okay, we'll discuss that when we solve some problems. But bottom line, what you need to remember is, in the small signal model, a new factor called RO comes in. What is the value of this RO? It's the magnitude of VA, which is a voltage that you may remember is like the early voltage. It's given for a particular technology and for a particular device, and you may remember lambda equals 1 by, I think, VA or some such relationship exists already. So RO is connected to VA, it's connected to lambda, and it's connected to the drain current. Okay, so RO equals VA by ID. Then you write the gain. Previously the gain was just VDS by VGS, which is GM into RD, right? But in this case you have to introduce this factor RO, okay, in parallel with RD. So the formula for gain, which was previously like this, a simple formula, AV equals minus GM by times RD on slide 54, now becomes modified to be AV equals minus GM into RD in parallel with RO. So assume there's an RD here that's in parallel with RO. So with this we can solve problems both with the effect of channel length modification and without the effect. Just to go back a couple slides so you can remember the alpha and the lambda business. Hold on. I have to go back. Yeah, here is another place where I show you the relationship between lambda and VA. VA equals VA prime L. VA prime is generally given, right? And then we find VA, it connects the length and this, and then we use lambda equals 1 by VA. So the same VA and VA prime are all what are being used in coming up with this value for this RO in the small signal model. Okay. All right, I'm going to have to move on to the next slide. Here we do just a little more about transconductance. I'm sure you know everything by now about transconductance, MOS transconductance, GM, but this is the order in the textbook, so I'm just following along. So this I brought in from the back of from the early parts of this chapter. Remember, we defined something called GDS, which was the name was just conductance. So don't confuse this with GM, right? GDS is just conductance. It also has the reverse of resistance. It has the opposite of resistance. 1 by ohms is a dimension, and it depends on all these factors. So GM is similar. I want to make the point that it's similar, okay, but it's a different thing also. So this Kn is still this, right? You recognize that. So Kn is still the same. V over voltage is the same. I guess I should have shown this to also be big. It's pretty much the same, but the way we look at it is somewhat different, and that's what you're going to see in the as you solve some problems. GM we associate mostly with only with small signal analysis. Okay, we don't talk about GM if there is only biasing being discussed. If we are only trying to set up a bias point Q, or we are only trying to find the bias current and VDS, big VDS, Then we talk about the conductance, and we may use it in a formula. But once we start doing small signal, where we are ignoring the bias, then we use the small signal symbol, the small gm, and but we still use some of the same other values, but nevertheless, to be clear, to separate the two, use the small gm. It's also the same slope relationship that you saw before is being repeated here. And we have all these formulas. I think maybe a new one came in. Maybe, I don't know if you've seen this before, but it is the root of, this kn times id, right? You take a square root, or you can split it up into this form. Problems come many ways, so it depends on the problem. And then gm is also written finally as this. So the derivation of these are in the text, but remember how to use these formulas, and as we do some problems you may become familiar. So last thing, a definition for GM. Now that we have read so much about the GM, what is GM? It serves as a measure of the strength of the device, meaning a higher value of GM means a greater change in the drain current for a given change in VGS. So if VGS changes slightly and you're told that you have two transistors, two NMOS devices, one has a higher GM, one has a lower GM, which one should you use? So if you pick the one with the higher GM, then for a given change in the input signal, the current will change more with the higher GM transistor, and the current ID will change less with the lower GM device. So that is what he means by a measure of the strength. Okay, I think we should be finished almost. I have a problem on slide 58. We'll come back to it. Slide 59, a problem, an example. On slide 5, I guess that's 60. So we'll skip that. Okay, at the very end, we have a couple more slides on the models, and then we are done. Okay, so give me 2 minutes. So the writer of this textbook introduces another model called the T equivalent circuit model. I haven't seen this in other textbooks, so I don't know how important it is. But anyway, he has given it to us, so let's understand it. So he takes the original hybrid pi model and he goes through some steps to come up with this model, which looks like a T. And this T, which is also shown to the right here, has, well, on the right side here, he brings in the RO, right? The channel length modulation resistor. So ignore that for the moment and just look at part D here. So what do we have? We have the three terminals, and still in the drain circuit, we have the same GM times VGS that we are used to in the past. But in the bottom, he has the same current flows, right? Because no current comes in from the gate, we know we are safe to say that there's only one current, and that is ID. So that flows all the way from the drain to the source. So how is he changing that GM VGS, which is a current? Here he has separated into a VGS and a 1 by GM. Okay, so VGS is a voltage, 1 by GM is a resistance. So if you multiply, well, 1 by GM is a resistance, so you divide voltage by resistance, you get current again. So there's some benefit to having this. I think he may show us in a problem later on, but this is a model. And then there is another model here to the right, where all he has done is he has taken this and applied the the resistor to the right. So basically, hold on, I'm going to just copy this from here to this, so that we know that these drawings to the right, they include the effect of the channel length modification. Okay, that means you add this RO. Again, I've not seen this too much, so hopefully we don't use it too much, but anyway, it's there. One last slide and then I think we are done. Here from another textbook, I found a summary of all the models. So there's 3 models for the large signal and 2 models for the small signal, and this is only the hybrid pi model. And you may notice he's written it slightly differently. The idea is the same. So there's a model for the A is the saturation region, open gate, current source, a controlled current source, dependent current source. This is called the triode region, again open here, but now the formulas are slightly different. And here he's also using the lambda factor. And then he's called the deep triode region, which is very low VGS. There we know that the whole device, the transistor, just can be modeled using a resistor, right? So he's shown that also. So all 3 are shown nicely in one diagram, and on this side he shows the small signal. This is big signal, this is small signal, and you see that same GM-VGS and the GM-VGS with an RO for inclusion of channel length modulation. Okay. So I hope this was helpful. Next slide is a problem, and then there's a summary of all these models, and this is the very last slide in my presentation. So we are done. So we are done with what we want to study in chapter 5. Of course, I'll do one more recording with problems on this amplifier and small signal, and we can finish. Okay, thank you.